Okay, great. Thank you for the introduction, and it's a pleasure to be here in Taiwan, and it's inspiring also to learn, more about what's going on in semiconductors here. Certainly, it's caught all of our attention is how successful Taiwan has been, and so today I'm going to tell you a perspective as a chemist, how we kind of integrate chemistry with electronics and to make sensors. And I frame this really in a way that is very similar to the way everything you know about that are the field effect transistor that's the basis of modern electronics. And I've always thought about it this way. I got very fascinated with field effect transistors back even when I was a graduate student. And so what I'd like you to kind of take away from this is some parallels, and I'm going to kind of maybe focus on things, a few kind of simple examples here, but hopefully you can see they're more broad than that, but how we can use molecular or biomolecular reactions or interactions to effectively do the same thing as your gate electrode does in your field effect transistor. That is to basically inject carriers or concentrate carriers into a channel region. I'm going to use organic semiconductive materials, so I'm going to focus on soft materials here today. There are things that we know how to interact with chemically, and they can be responsive. I'm going to also talk about excitons, which are optically generated quasi-particles and their transport, not just holes and electrons, but excitons, and show you how they can be useful to create a signal gain. And in general, the faster things move or the more readily things move, the bigger the signal gain. Just like if you have a higher mobility semiconductor, you can make a higher performance transistor. So a big thing that we focus on, and what the kind of a take-home message here is, that if you design the right materials, you can reduce the hardware necessities of your sensor. That is, we can make sensors with less and less sophisticated hardware, even though the hardware is changing constantly, but we can make inexpensive devices this way. And so the materials that we tend to deal with in our group, they're not atomistic. They're like a semiconductor. They're kind of lower dimensional materials because they really are kind of molecular or lower dimensional materials in nature. I'll tell you today about carbon nanotubes, which is an area that we work quite a bit with. We sometimes functionalize them by essentially sticking things to them in non-covalent networks, or sometimes doing sidewall chemistry on them. This is where each band here is 100 carbon atoms, and so sometimes we like to we talk about how many groups we put on for every 100 carbon atoms, and when we do these functionalizations. We also work with graphene and other two-dimensional materials. I won't tell you about those today, as well as conducting polymers. Conducting polymers are something that we've worked on basically since I've worked on since I was a graduate student for a very long time. Okay, so as I mentioned, we want our materials to enable sensors, and the whole idea here is how do we get away from these big laboratories where you have to have highly skilled technicians and very large expensive equipment, and do things that are field deployable. You can do them at the site and be done by people with very little skill, or basically they can pick up and just with a few minutes learn how to run a device. And I just give a couple examples of a couple of technologies that we have transitioned from our lab into the real world. One is an explosive detector. I'll just hit on this really briefly, but this has been out in the field now for 25 years, still used by a lot of, by the U.S. military and a lot of other countries to detect threats, and also in Homeland Security. If you're looking, police departments often will have these on robotic platforms to look at things, and it sniffs explosives. You can smell explosives with it. And we also developed ethylene detection systems that were used in cold storage rooms years ago through C2 Sense. And the advantage of having field deployable systems is now that we can basically have them out sampling in real time. We know where they are, what they're doing. If we can make smaller devices that we can put all over the place, we can get distributed sampling, and that's very important. But one thing I want to emphasize about chemical sensing is it's not as precise as a mass spectrometer, right? Mass spectrometer gives you exactly what you have. We're going to have things that it smells like this molecule, but if you have enough resolution in your chemistry, that actually can be very actionable and important information. So, as I mentioned, we're going to work with carbon nanotubes, and I'm going to tell you about those, and then I'll talk about semiconductor polymers a little bit later. But our devices with nanotubes are generally chemiresistors or chemitransistors. I'm not going to tell you about the transistors today, but that's just where we don't have the gate electrode attached. And the chemiresistor is a very simple device. We're just measuring the current that's flowing through this little nanotube network here between these two devices. And as Joel just said in the last talk, I mean, going straight from electrical signals is really good. You're not have any other steps in between. So the simplicity of an electrically resistive measurement is just hard to beat. And so that's something that's a real intrinsic advantage of these types of devices. Also, it takes very little power to make a resistivity measurement. It's probably even a couple orders of magnitude lower than microwatts in this. And in fact, as we make sensors that you can passively power through the RF coming out of your smartphones. We do passive RFID devices using our materials. And again, they can be very expensive and small. Big issue issues with these materials are generally it's not an issue, but they can be very highly sensitive. Selectivity has always been a big issue for chemiresistors. I would say this is something I think that our group has excelled on, mainly because we think about it from a very mechanistic standpoint and how we do this. And drift in the lifetime of these sensors is always going to be an issue. These are going to be sensors that you're not going to put out and have them go for years. They're things that are really going to be low cost and consumable. But I'm very excited about the future here because I think there is a real nexus. One of the things I like to say is all the electrical engineers are getting bored with only working with silicon, right? So they want to put other things into their circuits, and can they make large arrays with nanotubes? Can we start going, this is a device for my group we make just with a shadow mask and then we deposit on it. Can we start dreaming about having access to platforms that look more like real integrated circuits? And so when we think about our materials, I mentioned that we like kind of a mechanistic type of approach. When you think about these carbon nanotube arrays, we have to think about the conduction through the nanotube. What is the carrier population? Are we pinning carriers? Are we injecting carriers? Are we essentially compensating carriers? And I'm going to talk about that today. That's where we basically do carrier modulation. I'm going to talk about how we use transition metals to do that. But we also can do this through enzymatic activity, through reductases and oxidases. We also have made a number of sensors that actually focus on intermolecular, inter-carbon nanotube resistances. We haven't generally worried too much about the shocky barriers that happen between metals and semiconductors, but those can be an issue as well. So we're going to talk again, as I mentioned, about transition metals and how they work in these devices. And we have a kind of an expanding list of different things we've done with transition metals. They have the ability, they're catalysts. Chemists use them as catalysts. They are really important for creating the type of reactivity you want to detect these different expanding array of different analytes. And so I'm just going to touch on a couple short stories here today on the transition metals. And But in general, what we like to think about it is really kind of to take solution chemistry, what chemists use to make molecules, and then try and translate that selective process to give us a selective chemical sensor. And so we take these nanotube networks and we essentially put a solvent over the top of them, usually an ionic liquid, something that's not volatile. And that solvent, essentially we put a catalyst mixture inside that then can essentially either inject electrons or holes into the nanotubes. The nanotubes are naturally p-doped in air. They tend to, air physisorbs on them, so they're p-type semiconductors. And so if you inject electrons into them, you destroy the conductivity. If you inject holes in, you increase it. And so with that regard, I want to show you something. I'm not going to get too deep into the chemistry. This is actually the most chemical scheme you're going to get here today, but just to show you how you can take a reaction. It's a very well-known reaction. It was called the Heck reaction. It's what Richard Heck won the Nobel Prize for back in 2010. And it uses palladium to basically take, different organic groups here. This X group is what we call leaving group, something that goes away, and connect it to an alkene to make this new double bond. So what we did is we replaced that hydrogen with this R1 that began up over there. Okay, so this is a nice reaction. Organic chemists use this all the time. But what's key about this is this reaction cycle goes between two different forms of the palladium metal here. Okay, so we have palladium 0 up here at the top and palladium 2. So if we have a reaction, we take our little solution here, and we have in that solution, we have a bunch of this group. What would happen is anytime palladium 0 is generated, it's rapidly kind of sequestered over here into palladium 2. And palladium 2 basically is not redox active. It doesn't interact with the nanotubes. But if we give this material some of this substrate, it quickly reacts and zips around this pathway and generates a bunch of palladium 0. That palladium 0 is now a reductant. So we generate a reductant by action of this analyte here. Okay. Now the analyte of interest are acrylates and styrenes. These are monomers from the polymer industry. They tend to be toxic, and the OSHA levels around 25 part per million is what you're allowed to have with these. They're not good for you, and they are produced on 9 million tons per year. So they're around people who are working with plastics. It's something that's an occupational safety issue. So again, when we do this, palladium 0, when we generate it, what's it going to do? It's going to take these p-doped nanotubes. Again, air is doping the nanotubes, and it's going to basically push it over to this side and essentially compensate all those carriers and reduce the conductivity of the material. And as air comes in and basically, or this group here reacts, as this group reacts again and puts it back into palladium 2, we regenerate the conductive form on this side. Okay, and as I alluded to, this is a little more complicated than we have right here. We actually use molecular oxygen as part of this reaction as well, but that's actually nice because we want to do our sensing out in air. And so this is what data looks like out of this. This is with ethyl acrylate, a very well-known monomer that is used again on many ton scale. And this is showing what happens. This is the conductance through that, the normalized conductance through that simple little chemiresistor. And when we have our full catalytic system together, it's reversible. You see that we get a reduction, and when we quit this little dosing of the acrylate at 550 part per million, it comes back. And if we don't have our full system there, we just make palladium metal. It's irreversible. It's a dosimeter. It's not it's not a reversible sensor. And if we don't have all of our full catalytic mixture intact, we don't get a response. So we have a way of actually generating nice sensors with a catalytic system that does this, and it's very selective. So this is where I'm showing that if you look at metal oxide sensors that are used for gas sensing. People say they're selective if they get, say, a 20, you know, a 100% difference between one signal and the other. Here we're seeing orders of magnitude difference between our acrylate and other very similar molecules here, okay, that we have. And these are all at 4 times the 5 times the constant, 4 times the concentration, of this 50 part per million sample here. These are at 200 part per million. So it's a very selective sensor, and it's derived from strictly the chemistry. Now, acrylates are toxic monomers. This is something that's relevant to occupational safety, people working around these. But we are also interested in other alkenes more relevant and other gases relevant to agriculture. I won't talk about amines here today, but ethylene is a small molecule. It's just, 2 carbons, 4 hydrogens, a very, very small molecule, but it happens to be a universal plant hormone. It controls the ripening of fruit. And so if you want to actually understand ripening processes of things, you can use ethylene as a proxy for that. And I think you've all heard about how bananas give off a lot of ethylene. You want to keep them away from your other fruit because they'll cause the other fruit to ripen prematurely. Ethylene tends to synchronize the ripening of fruit. And so it's something that you really would like to be able to measure, whether it's in a greenhouse or in your grocery store. And we have done this previously with fruit ripening, but more recently we decided we wanted to get more sensitive sensors that actually could even essentially detect ethylene levels that can cause flowers to bloom. So flowers tend to be more sensitive to ethylene than fruit. And so we did a study with carnations and different flowers. And the chemistry that we used, again, was some of the same palladium type chemistry. This mechanism is a little more complicated than the one I showed you before. But we used something, kind of a modification of a classic reaction called the Walker reaction. And again, this reaction, when we have ethylene present, ethylene makes a bunch of palladium 0. Over here, it undopes the nanotubes, and then we do this in the presence of molecular oxygen, and the oxygen brings it back and resets the carbon nanotubes. So ethylene burst, conductivity goes down. When the ethylene's gone, oxygen takes it back to a higher conductivity. So we basically get these same types of results. This is the same sort of data I showed you before that Daryl, the student that put this together, liked to plot things upwards, so he put a negative sign here, but it's a decrease in conductivity. And you can see here that, this is a signal down at 500 part per million. Our limits of detection are quite a bit below that. In this case, there's a couple other little tricks we had to do. This is with nanotubes. We had to put pyridyl groups onto the nanotubes that basically help to immobilize the catalyst on the nanotubes. So we often do chemistry on the nanotubes, just when I showed you before that we put about 1 group for every 100 carbon atoms, so we still maintain a lot of the conductivity of the nanotubes while doing these types of experiments. And again, here, when you do these things the way we're doing it, we have really good selectivity. Okay, these are a bunch of kind of chemicals from our solvent cabinet. But nevertheless, I think you can see that this is very specific for ethylene and alkenes. Okay, so I want to transition to a little different technology now and show you the kind of the advantages that you can have with organic semiconductor systems as optical sensors. And what we're going to look with is organic molecules that have what we call a pi electron system. So you have delocalized electrons, and these electrons are highly polarizable. And organic molecules like that have some of the highest, have essentially the highest optical, coupling that you can get really from these types of, for at least from non-metallic materials. And they're used widely. They're why your OLEDs are so bright. Those are organic chromophores that are giving you that bright color of your OLEDs. You can make them absorb strongly enough that you can make solar cells that are so light you can put them on top of a bubble. So this is out of Vladimir Bulovich's lab at MIT. You can make a solar cell that can absorb light that thin, whereas you had a silicon solar cell, it'd have to be a lot thicker than that. They're the brightest dyes used in flow cytometry. Any of you that do high-performance flow cytometry are using organic polymers based on kind of methods I'm going to show you here in just a bit, and also, you know, dyes and pigments. Of course, the brightest dyes and deepest colors are always organic materials. And so in that context, we have worked for many years on the optical properties of our polymers. And I'm just showing here kind of a band diagram, kind of in a spatial dimension with some sort of, you know, schematic of what a polymer might look like. And this polymer I have shown here has little receptors on the side that will bind whatever, you know, different groups you might be interested in. And so these are direct band gap semiconductors. That is, it's an allowed transition. They're highly fluorescent, quantum yields near unity. And if you excite them with light, you'll generate electron-hole pair. They're stuck together in a quasi-particle called an exciton. That exciton can move about, and if it doesn't find anything else to do, this electron will just come back down and it'll give off a photon. But if it runs into the red balls here, you'll do electron transfer out to the red ball and back again. That is, the red ball has a state in the middle. We can do a similar thing where we get, you know, electrons essentially from the yellow ball to come in and go back. These both destroy the luminescence, or we can actually also have an analyte bind and create a new band gap, a lower energy band gap that will trap the hole. The hole will, like a balloon, will rise up because it's backfilling the electrons behind it, and the electron gets trapped because it's lower energy. And so these are things that have been used, that we've used widely. We've invented this technology a very long time ago. It's widely used. There are thousands of examples of people have used these types of methods. But in our case, what really kind of put this method really on the books was, again, our explosive detection schemes. And in this case, what we did is we just showed that you can make films of a polymer. This is the semiconducting organic polymer. This is the pi system along the backbone here. And it had these little wings on it that creates a nanoporous environment that only lets small molecules in and prevents self-quenching of the polymers. It keeps the polymer chains apart a little bit. And this ended up being a very good sensor for the explosive TNT. And so the way to think about this is a photon comes in, it creates an exciton. The exciton does a random walk, it migrates around. This random walk, this exciton can visit around 20,000 potential binding sites. So it gets to look around at 20,000 sites, and if any one of those sites has TNT in it, that exciton is essentially dead. It's quenched. And so this gives a very, very, very sensitive quenching mechanism for TNT. These handheld devices can detect about 1,000 molecules of TNT. They're still the most sensitive explosive detectors 25 years after we've made them. They're about 1,000 times to 10,000 times more sensitive than the benchtop systems you find in airports. And again, they can sniff TNT, and so they're widely used and still commercial under the trade name FIDO, which is owned by Fluor Systems. Now, I want to tell you today a more recent topic in using the same methodology to detect PFAS. So PFAS is, again, it's a health issue. It's something the semiconductor industry actually has a PFAS problem because we use it in our processing, whether you're doing, you know, dry etches with fluorine or you're part of your photoresist. There are PFAS emissions coming out of semiconductor plants, and the U.S. has actually, you know, got quite ahead of the curve on this in terms of the APA putting out different specifications. In general, what they want is an enforceable limit in drinking water of up to 4 part per trillion, excuse me, of these two chemicals, perfluorooctanoic acid and perfluorooctosulfonic acid here. Now, the way we go about doing this is a little bit different than the TNT. In this case, we're going to essentially create that little dimple in the band. We're going to create that new emitter with the PFAS, and we make use of a charge transfer type transition in these materials. So in this case, we use a material that has fluorocarbons in it, so it's a sponge. It selectively absorbs PFAS. It does not react with any organic acids. And when it absorbs PFAS, what we do is we shift this charge transfer transition to the red, because this now, when this is protonated here, this is a more stable, excited state. And so what we get is we get ordinarily a blue emission, but when PFAS is there, we get a green emission. So we excite this, we have the exciton migrates around. If it finds PFAS, it gives off a green photon. And again, this is the same mechanism that I said here. This is where we use these different pyridine groups as our, what we call our selector groups. And this is, we're creating this new little dimple in our band gap here with PFAS. And to show you what that looks like, here is an example of some nanoparticles in solution and their exposure to different concentrations of PFAS. And you can see here, you can see without any PFAS, it's a very deep blue emission. It becomes teal at 500 part per trillion, and at 10 part per billion, it's essentially all green. And what's important about this is this measurement is also ratiometric. We're getting a decrease in the emission at the primary band gap of this material, with an increasing emission of that new emissive signal that is due to the protonation of this pyridine by the PFAS. And that ratiometric thing gives us now a way to quantify materials. And again, it's completely selective for PFAS. Now, this method can get down to part per trillion detection limits in around 30-second time frames. That's with no pre-concentration. There's no other system that comes close to this in terms of sensitivity out there. And as a result, we're commercializing this through a small startup called Fluoridics. This is just kind of what it looks like. We're essentially using kind of dipsticks right now that look like pH paper, but we actually only mix with the PFAS contaminated water for 30 seconds because we figured that people will go and check their smartphone if we don't give it longer than that. So we actually only have a 30-second incubation, and that's how this works. And we're hoping to get this in testing groundwater and people's and municipal water supplies as soon as possible. So I want to just kind of end here with that molecular structures and reactivity are very important for sensing. Soft electronic materials, really, there's a lot to do with them. They are a really important interface to kind of plug into semiconductors. I showed you here chemical methods, but it's equally applicable to biochemical methods. And getting strong signal transduction and selective signal transduction as a result of chemistry is critical. And like many others, I have a kind of a great group of people that are all working hard to make this work. And this is just a recent picture of my research group at MIT with a great dome behind us. Thank you.